In this video, we're going to look at another way that we can use ice tables to solve for a different quantity. So this time we're going to be solving for our equilibrium concentrations if we don't know any of them. So in this case, we need to already know the value of K as well as our initial concentrations. So we need to know initial concentrations and the value of K in order to be able to solve for all of our equilibrium concentrations. So in this case, we're going to set up our ice table just like we have been. And write our equilibrium expression. This time we won't have values for our equilibrium concentrations, but we will have expressions all in terms of X. So when we write our ice table, we put everything in terms of X using the stoichiometric coefficients to indicate the relative amounts by which our concentrations are changing. And at equilibrium, we usually have something plus or minus X as what's left over at equilibrium. So we take those expressions and plug them into our equilibrium expression. And since we know the value of K, that will allow us to solve for X. The only unknown in our equation will be X, and we can solve that. And then we can plug our value of X back in to our ice table to find the concentrations. So if we look at a relatively simple example, just generic reaction here, if we have 1.5 molar A that reacts according to the equation above, actually you're going to make a slight change to this. Equation below, rather. If KEQ, the equilibrium constant, is equal to 57.4, what are the concentrations of A and B at equilibrium? So, first thing we want to do is set up our ice table with all of the information that we know so far. So we are told that we are starting with a 1.5 molar solution of A and no B. So as this runs towards equilibrium, it's going to go in the forward direction. Because we have no product initially, we need to create some product and we will consume some reactant to do that. So our product concentration is going to increase, our reactant concentration is going to decrease. 1 mole of A reacts to form 2 moles of B. So for every X moles of A, or molarity of A that we consume, 2X molar B will be produced. So at equilibrium, if we started with 1.5 and we used up X, we will have 1.5 minus X remaining. For B, we started with nothing and we created 2X. So we will have 2X molar when we reach equilibrium. So now we need to take these expressions in terms of X and plug them into our equilibrium expression. So if we write our equilibrium expression for this process, we get 2B on the top. So B is going to be squared. And then our concentration of A will be on the bottom. So we were given the value of K in the problem as 57.4. We don't know the numerical value for our equilibrium concentrations, but we know that the concentration of B is equal to 2x at equilibrium, and the concentration of A is equal to 1.5 minus x at equilibrium. So if we plug in all of those things, K is 57.4, B is 2x, and that is still squared. A is 1.5 minus x. We now have this equation that only contains a single unknown variable, x, which means that we can solve this. So you are going to end up solving a quadratic. So we need to get this into typical quadratic form. Really, I don't care how you solve it from this point. Whatever mathematical method you want to use is more than fine by me. So whatever you do from here is kind of personal choice, but what I would do is get it into ax squared plus bx plus c equals 0 form and go from there. So if we want to do that, I would first square this top term personally. Remember that you are squaring both the 2 and the x. So 2x squared is 4x squared. And then we have this 1.5 minus x on the bottom. So if we multiply both sides by the denominator, we'll have 57.4 times 1.5 minus x is equal to 4x squared. So if we distribute this 57.4 to both terms inside the parentheses here, we get 86.1 minus 57.4x is equal to 4x squared. Now we just need to end up with everything on the same side. It doesn't matter which way you go about that. If we move these two terms over to the right, we get 4x squared plus 57.4x minus 86.1. So we're in typical quadratic format here. From here, you can do it out in your calculator the normal way, or you're welcome to use a quadratic solver program or website. It's totally fine with me. You can also graph it and look for the intercepts. But when you solve this, however you solve this, you will find values for x, solutions for x of approximately negative 15.7 or about 1.37. So quadratics have two solutions to them. In science, there is only one right answer. So only one of these is correct. And the question is, how do you know which one? So there are two things to look for. X can never be negative. And X can never produce negative equilibrium concentrations. So what I mean by the second one is if you take your value of X and you plug it back into your table, you can't come up with a negative answer. Negative concentrations are impossible because we can't have negative moles, we can't have negative molecules. So the results we get here have to be positive, and X itself should be positive as well. If you come up with two negative X values, you did something wrong. You might have your reaction running in the wrong direction, which would make your answers correct, but the sign wrong. But X should be positive if everything is done correctly, which is all we need to look at here to identify the correct choice as being 1.37, since our other option was negative. That one is a no-go. So our value of x is 1.37. Now, you need to remember what the question actually asked you. Most common mistake I see on these problems is after you've done so much math, you're like, I solved for x, I must be finished. But you were asked here, what are the concentrations of A and B at equilibrium? Neither A nor B is equal to x, so you are not quite done yet. The last thing you need to do is take your value of x that you have found and plug it back in to your ICE table to find your final concentrations. So the concentration of A at equilibrium we know is 1.5 minus x. It's going to be 1.5 minus 1.37 gets us 0.13 molar, and the concentration of B at equilibrium is equal to 2x, so that is 2 times 1.37, which is going to be 2.74 molar. So these are, choose a color we haven't used yet, these are our final answers. Our concentration of B and our concentration of A is what we were actually asked to solve for here. So I would like you to take a couple minutes and try this one on your own. Notice that we are in pressure instead of molarity. We can plug in those exactly the same way. Pressure and molarity are effectively the same thing for gases, just expressed in terms of different units. But we can use pressure in an ICE table exactly the way we would molarity. You will notice that this is labeled, our equilibrium constant is labeled Kp, just means it's in terms of pressure instead of molarity. Numerically, they are different, but functionally, they're expressing the same idea. So nothing fundamentally changes here except what your units are labeled as. So give this one a shot on your own. At least try to get through the setup. The math on this one gets a little dicey, but we'll walk through it together. So we're going to set up our ICE table in exactly the same way that we have. Initial, change, and equilibrium. We are starting with 3 atmospheres of NO2 and none of our product, which means we are going to need to produce product and consume reactant to get to equilibrium. And our coefficients in our reaction tell us for every x atmospheres of N2O4 we produce, 2x atmospheres of NO2 are going to be consumed. So once we reach equilibrium, we will have 3 minus 2x atmospheres of NO2 remaining, and we will have x atmospheres of N2O4 that we have produced. So now we need to take what we know and plug it into our equilibrium expression. So our equilibrium expression, products on top, is N2O4, reactants on the bottom, NO2, which has a coefficient of 2, so it gets squared. So we know the value of K, we're given that in the problem, and we have the value, the amount equilibrium pressure of N2O4 expressed as X, and the pressure of NO2 at equilibrium expressed as 3 minus 2x. So if we plug all of these things into our equilibrium expression, our concentration of NO2 down here, concentration of NO2 up top, and that expression is equal to the value of K. So we have 9.3 times 10 to the minus 7th is equal to 3 minus 2x squared on the bottom times with x on the top. So now, once again, we need to solve the quadratic equation. And just the way the numbers are arranged in this one makes it a little bit more complicated. So how you get there is personal preference. Personally, the first thing I would do is expand the squared term here on the bottom. So I'm going to have 9.3 times 10 to the minus 7th. When I square that 3 minus 2x, I'm going to get 9 minus 12x plus 4x squared is my denominator. And I've still just got x on the top. So we're going to need to multiply both sides by the denominator. So we still have k is 9.3 times 10 to the minus 7th, and that is going to be multiplied by the entire denominator. 9 minus 12x plus 4x squared is all equal to x. Now we need to distribute this to the three terms in here. So we get, I'm going to rearrange things a little bit as I do this, just to put them in a more friendly order. So this times the x squared term is 3.72 times 10 to the minus 6th x squared. K times the x to the first term gives us minus 1.12 times 10 to the minus 5th x, and then this times 9 is plus 8.37 times 10 to the minus 6th. I guess I put it over there, but I'd really rather have it on the other side. This whole expression is still equal to x. So the last thing we need to do to get this in typical quadratic form is just subtract this x from both sides so that that is equal to 0. So we will have 3.72 times 10 to the minus 6th x squared. When we take this and we subtract 1 from it, it's essentially -1. This is a small enough number that technically it would be minus 1.0000112, but that's close enough to 1 that we can ignore the difference and just say this is minus x, that our coefficient here is -1 essentially, plus 8.37 times 10 to the minus 6th is equal to 0. Now we can solve for x however you like to solve quadratic equations. Math happens here. And we should find that x is either 268,817 or 8.37 times 10 to the minus 6th. So again, with quadratic equations, we always have two solutions, but there is only one correct answer in science. So both of our values here are positive, which means there isn't an obvious choice. We said x can't be negative, which is usually pretty straightforward to identify, but both of our x values are positive. But if we think about that other constraint that I mentioned, that x can't produce negative equilibrium concentrations, also can't produce negative pressures. If we think about plugging this value in here, 3 minus 2 times this is over -500,000. So that is an extremely negative concentration that this would produce. So this guy is out. This is our correct value of x. And now we want to think about what is the question actually asking us here. we were asked to find the concentration of N2O4 at equilibrium, which conveniently in this case is X, so we are actually done. So this is equal to my concentration or my pressure. Sorry, this one's in pressure. So I shouldn't use the square brackets. Not a big deal. But this is the pressure of N2O4, which is what we were looking to solve for.